Second section of chapter 10 is on liquids. And liquids, as I've defined here, is the least common state of matter in the universe. And the reason for that is because liquids need this narrow range of conditions in order to exist. We are very used to liquids because of these narrow range of liquids, is a narrow range of temperatures and pressures is basically what we're up against here on the planet Earth. So we notice a lot of liquids. Okay, but essentially having frozen methane, which is a frozen gas, frozen carbon dioxide, frozen water, these are all different types of substances that are going to be in the solid state if we have different conditions. Okay, now, in this section, you should be able to describe the motion of particles in liquids and the properties of liquids according to the kinetic molecular theory. So this goes directly back to section 1. Now, we talked about the KMT. We defined it. We gave the 5 assumptions in section 1. Then we talked about the KMT and as it applies to gases. We're going to talk about how the KMT applies to liquids in this section. Discuss the reasons why some liquids can evaporate to a gas, and then we'll discuss freezing very, very briefly. Okay. So liquids. Last section we talked about how gases have an indefinite shape and an indefinite volume. Well, obviously liquids have an indefinite shape. They can move around, they can swish, but they can't expand to take the shape of their container. So they do have a definite measurable volume, always a definite measurable volume. The particles are closer than gases. As a matter of fact, the difference between particle closeness from liquids to solids is negligible. We consider them to be both compressed or condensed states. Particles can slide past one another. I think that's self-explanatory. Obviously, if they're in the liquid form, if we take a look at point number 4 here, the attractive forces must be stronger in liquids than they are in gases. Now we don't just have London dispersion forces, but now we have dipole-dipole forces and rather strong hydrogen bonding. We talked about both of these properties, these hydrogen bonding or intermolecular forces in chapter 6. So as far as the attractive forces goes, because they're in a more condensed state, the attractive forces between liquids or any two liquid particles is stronger than those that are in gases. Next, liquids have more order due to their strong attractive forces, thus they're in the liquid state. That goes directly along with this 4th point, so the 4th and 5th point go together. And we would describe liquids as fluids, liquid particles that are in constant motion, particles that can slide past one another. Okay, so if we take a look at the molecular view of these things, we see that these particles, they're in the condensed state, they're very close to one another, and because they have strong attractive forces, but they can slide past one another. We also know that these strong attractive forces can be overcome to get evaporation, so we'll talk about that too. All right, next, let's talk about some properties of these liquids. They have relatively high density. Of course, we know that according to the, not according to the kinetic molecular theory, but if we take a look and compare and contrast these to the gas state, we see that the gas particles are 1,000 times more, have 1,000 times greater volume than the liquids do. Why? Because liquids have greater forces of attraction. So most substances are less dense in liquid than they are in solids. Okay, water is the exception. So the high density of liquids versus the high density of solids has to do with particle position. They also have to do with particle density, and therefore most liquids are less dense than their respective solids. The exception that we know of is water. Whether there's more exceptions out there, I'm not sure of, but water, let me say it this way, most particles, most solid substances will sink in their respective liquids. Water's solid, ice, floats on its respective liquid, water. Okay? Liquids are relatively incompressible. Particles are already close together, so you can't squish them like you can squish gases. Next, liquids do have the ability to diffuse. Even though it's a condensed state, even though the particles are very close to one another, we know that they can slide past one another. These particles are in constant, random, rapid motion. So liquids, it is slower. Diffusion is slower in liquids than it is in gases because the particles are closer to one another. But basically, if you were to go to a swimming pool and take bright red dye and throw it in there, it'll diffuse and take up the whole pool. And so the whole pool might appear to be red. It depends how big the pool is and how much dye you used initially. But essentially, they would diffuse and it would take a little bit longer than it would take in a gas. Now, if I were to heat up the pool, if I were to take like a 100 degree Fahrenheit pool versus a 50-degree Fahrenheit pool, I would notice that the rate of diffusion is much faster in a 100-degree pool than it would be in the 50-degree pool because the kinetic energy of those particles is greater. So the movement, the motion is much, much greater when it gets warmer than it is in slower, the colder temperatures. All right, properties of liquids, still talking about that. We have surface tension. Now, surface tension is a force that pulls adjacent particles of liquids at the surface together, decreasing the surface area to the smallest possible size. This is due to the strong attractive forces. All right, so what I would expect on surface tension, if we take a look at the next slide, you'll notice that here in this droplet of water, be due to surface tension, which is the ability of the particles at the surface to draw close to one another, I have the smallest possible shape here in the droplet that's actually coming up from the drop or the drip there, whatever you want to call it. But that's surface tension, okay? Um, these are due to, of course, again, the strong attractive forces. The next thing I have is, again, a property of liquid is something called capillary action, which is the attraction of a surface of a liquid to a solid. This is actually what plants do to get water to the top of the trees. So all the cells are stacked on top of each other like this. So here's a plant cell, a plant vessel, vascular tissue. And what happens is water is drawn up from the bottom and moves up from cell to cell very slowly, but it works. It actually goes against gravity. So capillary action is something that can actually fight gravity to an extremely tall height in some of these trees. Some of these pine trees that we have outside the school are 30, 40, 50 feet high. And of course, to get water to the top, we need capillary action to do that. Okay. Next, evaporation. Evaporation or vaporization is the process by which a liquid or solid changes to a gas. Okay, I think that's pretty self-explanatory. Now, evaporation has to do with particles escape from the surface of a non-boiling liquid and enter the gas phase. Now, the way we have this, or the way we see this, let me see this. Okay, we're almost done here. But the way we have it is this. If I have a number of particles, so here's number of particles, and here's their kinetic energy. Most of these particles are like this. Okay, so let's say this is about 25 degrees Celsius. So most of the particles are at 25 degrees Celsius. But you'll notice that a small fraction of these particles, somewhere down here, these particles, again, there's not many of them. The number of particles are very small, but they have an extremely high kinetic energy. In other words, they have extremely high temperature. So the particles that are available to evaporate or vaporize are particles that are at the extreme of this bell curve. Consequently, these particles down here are close to freezing. These particles up here are close to being in the gas phase. So it's only these particles here that are available to go into the gas phase. And lastly, for section 2, we have freezing, which is changing from a liquid to a solid. And in order to do this, and we'll talk about this more as the class goes on, but just as an introduction, removal of heat is required. This is something called an exothermic process. You need heat to be removed or to be expelled out of the system in order for freezing to occur. Okay, and then of course we have the more ordering of particles and so on. Okay, all right, that's section 2.